Robo. Hazard detection and localization for health and safety patrol robot. Project sponsor Rolls-Royce Singapore Private Limited. Support provided. Robot hardware. Test area for data collection and vehicle testing. The manufacturing shop floor in Rolls-Royce is an environment where operators and engineers are constantly dealing with heavy machinery, tools and dangerous chemicals. There is a need to elevate the current health and safety standards to the next level to reduce occurrence and severity of workplace injuries in the company. According to the 2021 and 2022 data from the Rolls-Royce Health and Safety Team, approximately 40% of the hazards flagged up are trip hazards, which arises from the incorrect placement of objects in the office or manufacturing shop floor area. We are tasked to build a robot which can perform the following tasks. Firstly, the robot should be able to do trip hazard detection and classification for various trip hazards such as boxes, fixtures and media bags, which are typically found in a manufacturing workplace. Secondly, the robot should be able to identify the location of the hazard detected and finally output this information as a summary report after the patrol. The project deliverable would be to build and showcase a robot which is capable of patrolling a fixed path in the Rolls-Royce pre-production facility and compile a hazard summary report for the HSE team to review and follow up. Literature review. In this article, the authors mentioned an important challenge regarding hazard detection is that the same object can be considered as a hazard as well as not a hazard, depending on the orientation of the object as well as where the object is placed. The authors proposed using multimodal approach to tackle this problem and conducted an investigation combining color and depth information using different fusion approaches. Instead of using a feature matching algorithm, the authors in this article tried to use a deep CNN architecture where the convolutional and pooling layers are used as feature extractors and the fully connected neural network layers are used for location classification. Our proposed approach is to remote control the robot to move around and capture video of the facility and extract frame by frame and pass it to two models. A place recognition model to identify which room the robot is in and an object detection model to identify our object of interest. Once the object of interest is detected, we'll take a patch below the object and pass it to a binary classifier to determine if the object is in a safe or unsafe region. If it's in a safe region, it's not considered a hazard. Else it will be flagged as a hazard. Lastly, we'll combine the output result using a rule-based approach to generate a report indicating the type of hazard and location where the hazard is found. In order to train the models highlighted earlier, we need to prepare the relevant datasets. Our three-step data pipeline includes three main steps: data collection, data labeling and data augmentation. For data collection, the Yahoo Master X3 robot is used and it is equipped with the Astra Pro camera that is capable of capturing videos with a resolution of 640 by 480 at 30 frames per second in RGB format. To collect representative image data, a wireless controller is used to remotely guide the robot around the office and lab area of the pre-production facility where typical trip hazards such as a box are placed in different areas and orientations. While the robot is being guided around the facility, the RGB stream from the Astra Pro camera is saved as a video and frames are extracted from the video at a fixed interval for data labeling and augmentation. In total, 16 videos were recorded and 430 frames were extracted from the recorded videos. For data labeling for object detection, we used an online tool called Robo to do the object annotation for all the frames extracted. For this project we have opted to do three types of objects: box, fixture and media bag, which are typical objects found in the intelligent process lab and office area. For the unsafe region classifier data labeling, we extracted the patch below the object and assign it to the respective folders. For example, for objects that are placed in a safe region, we extracted the patch below the object and assign it to the folder named safe and vice versa. We were able to extract approximately 150 patch images per class, with the images being highly diverse in terms of location and orientation. For our vision-based place recognition model, we have assigned approximately 150 diverse images of each location to its respective folders. Office and Intelligent Process Lab. We decided to try out some of the data augmentation techniques available in RoboFlow to have a variety of data. The dataset and labels are then downloaded in a YOLO trainable format for model training. The data augmentation strategy is also extended to the unsafe region classifier and localization models. We settled on two sets of augmentation for the unsafe region classifier and localization. As was the case for object detection, this creates 6 additional augmented images per original image, causing our total dataset size to expand from 300 images to 2,100 images. Model training and evaluation. YOLO V8 being a single-stage detector is faster compared to two-stage detectors. It is also an anchor-free model, and YOLO V8 also has better accuracy as compared to previous versions of YOLO models. YOLO V8 architecture for object detection consists of two major components: the backbone responsible for feature extraction and the head responsible for processing the feature maps generated to predict bounding boxes and objects. We adopted the transfer learning approach and used the pre-trained YOLO V8M model as our base and further trained it to detect our object of interest. Our overall object detection model achieved a mean average precision 50 of 90.1% and a mean average precision 50 to 95 of 81.3%. As CNN is great for image classification and yields fast and accurate results, we opted to use CNN as the model architecture for both the unsafe region classifier and the vision-based localization model. Unsafe region classifier. For our unsafe region classifier, the dataset was split into 80% training, 10% validation and 10% test, and we have experimented with different combinations of layer structure and hyperparameter values. On the left, the graphs track the changes in model accuracy and loss on both the training and validation sets. Evaluating the model on the test set shows that the model is performing well in terms of F1 score and accuracy, but the precision for safe region is relatively low. Additional logic to alleviate this issue. Place recognition model CNN. We split the dataset into 80% training, 10% validation and 10% test prior to model training, and experimented different combinations of layouts and for the place recognition model. The graphs on the left indicate that the model is very stable and negligible degree of overfitting observed, as shown by the confusion matrix and performance metrics such as accuracy and F1 score. The model performed exceptionally well on the test set. As the precision for Intelligent Process Lab and Recall for Office is not 100%. It seems that there is some flickering between the locations while the robot is moving around the pre-production facility. We added additional logic to the code to alleviate this. Overall system performance evaluation. We have designed our test cases to cover a diverse variety of scenarios such as detection of different objects, different locations and different placement of objects, which would determine whether an object is a hazard or not. As shown in the table, the system was able to pass all the test cases.
This is the test case 1 scenario where we have placed a box on the office table, and this does not constitute as a safety hazard. As you can see, the object is correctly identified as a box, and the green bounding box indicates that the box is placed in a safe location and therefore not a hazard. Also, looking at the top right hand corner, the location predicted by our image-based place recognition model is the office, which is in this case a correct prediction. As the robot enters the Intelligent Process Lab, the location tag changes from office to the Intelligent Process Lab, and the system correctly identifies the fixture and places a red bounding box around it to indicate that it is a hazard. It saves a snapshot of this hazard, and this will be presented in the summary report later. The robot then continues on its fixed path, checking if there's any other hazards along the way.
A sample of summary report is as shown, consisting of information on the hazard detected like timestamp, hazard type, location and an image URL. In conclusion, a scalable and automated hazard detection system to drive down instances of near misses and workplace injuries have been successfully developed, and it showed great performance on the test set in terms of precision, recall, and accuracy scores. Future work. Firstly, increase the scope of potential hazards applicable to the manufacturing plant. Secondly, incorporate SLAM in the robot to replace vision-based localization for improved performance and autonomous navigation. Finally, incorporate real-time alert notification with industrial IoT platform. We have reached the end of our presentation. Thank you.